Hi everyone, we're going to have a look at the binomial distribution in this video. So unfortunately this might be quite a long one, so do bear with me. It's quite complicated, the binomial distribution, as this is probably your first sort of delve into distributions in AS statistics. It's all about working out probabilities for events. So we will have a look through everything to do with the binomial distribution, how to set up a question and how to go about getting the probabilities for a variety of different questions. So this is what we're going to cover. We'll have a look what probability distributions actually are, and then we'll go. Oh god, I fucking. Hi everyone. We're going to have a look at the binomial distribution in this video. So unfortunately this might be quite a long video. There's a lot to go over in the binomial distribution. It's quite complicated because we need to go over what distributions actually are to start with, since you probably haven't seen them in statistics before. But they're all about figuring out probabilities for various events. So we'll look at a whole range of questions here and how we can answer all the different styles of exam question. So this is what we're going to go over. We'll have a look at probability distributions first, what they are, different types of distributions and where the binomial distribution fits in, when we can actually use the binomial distribution, what conditions there are for when we can use it, a few examples, and just how. And after that, basically, it's just how to formulate questions and how to go about answering them. So there's loads of content here, and there's a few different ways in which we can answer binomial distribution questions. So we'll have a look at a full range of questions. Okay, so probability distributions. They help us model statistical events. Okay, so all these type of events we've been looking at in tree diagrams and things like that, we can normally use distribution to help us figure out what the probabilities are. Now the binomial distribution is a discrete distribution. Now there's two types of distribution. There's a discrete type and a continuous type. And we'll have a think about what the difference between these are. Now, binomial fits in here as a discrete distribution. An example of a continuous one is the normal distribution. We don't do that this year, so don't worry about that. But we'll talk about what these can be used for. Now, continuous variables are things that there's no limit to the precision we use when we measure them. For instance, they can be things like height or weight. So a height can be any value. It can be 184.27 centimeters, 188.98436 centimeters. It can go as precise as you like, and there's no end to the number of decimal points on the end of it. If I could measure accurately enough, it would go on forever. It doesn't just take integer values. Discrete distributions, on the other hand, only take certain values. Okay? So often these are integers. So discrete only takes certain values. That could be things like, so number of times a coin lands on heads. Yeah, so that could either be 2 or 3 or 4. It can't be 2.5. It can't be 2.37. It has only limited values it can take, whereas continuous can take any value at all. Now that difference is quite key, and it changes which distribution we would use to model it. So the binomial is good for these discrete events. So another example is how many times a dice lands on 6, or the number of children in a class who have asthma, for instance, is a fixed. It's got only certain values it can take. It could be 2, it could be 5, it could be 7, but it can't be 6.25 or whatever. It has to be an integer often. But anything where it can only take certain values will be a discrete distribution. So we'll talk a little bit about the notation now, about random variables. It's important to get your head around this because this is something people tend to struggle with. So try and spend the time getting used to what all this stuff means, and it will make answering the exam questions a lot easier. It is well worth spending some time trying to understand this. So capital letters, and we often use X, is what we call for the binomial, it's a discrete random variable. That means it can take different values depending on the event we're modeling and depending on the outcome of that event. So for instance, if our event was, let's say, I'll not write it there because we've got another line coming. If we say X is number of times a coin lands on heads, okay, if it's the number of times a coin lands on heads, X could be maybe 3 or 4 or 5. It depends how many times. If I say it's the number of times a coin lands on heads, if we throw it 10 times, there's a set of values it could be. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. Okay, so it kind of holds the outcome of our event, and it can be any of those values. So there's a kind of list of values it can be. So that's what a discrete random variable is. It can take a set of values depending on what event we're looking at. So yeah, so the probability X equals 2 is the probability that the outcome of our event, X, whatever it might be, so the number of times a coin lands on heads, for instance, is 2. Okay, so it holds the outcome of our event, and we can work out probabilities associated with that. So when can we use the binomial distribution? We've said it has to be a discrete distribution, so it has to be for something that can only have certain values as its outcome. But what other conditions are there? There has to be a fixed number of trials. Now, in that example I've just given about tossing a coin, it means that we say we throw a coin 10 times. That would be a fixed number of trials. Or we roll a dice 25 times. Again, a fixed number of trials. Or that there are 25 people in a class, and we're looking at the probability for each of them. Again, that's a fixed number of trials. It's a fixed number of people. It doesn't work when we'd say something like we roll a dice, and if we get a 6, we roll it again, because the number of trials there isn't fixed. It can vary depending on the outcome of the previous trial. So to use the binomial, we have to have a fixed number of trials. Each trial has to have 2 possible outcomes, success or failure, broadly. So the coin one, we'd say the number of times a coin lands on heads. Heads would be a success, tails would be a failure. Okay. The way in which we define a success or a failure is up to us, but there has to be only 2 possible outcomes. Now, if you think about a dice, you might think, oh, well, there's 6 possible outcomes there, but all we do is say our event is the number of times a dice lands on 6. Getting a 6 is a success. Anything else is a failure. So you can either have 6 or not a 6, and they're the 2 possible outcomes. So we have to be able to split it into 2 possibles. So in the class example, again, it could be 2 outcomes, whether a child in a class has asthma or doesn't have asthma. It has 2 possible outcomes. We can't use it when there's several different outcomes we're trying to model. It has to just be this or not this. Okay, just 2 possibles. Okay, the probability of the trial being successful has to be the same for each trial. So this is really important. So a coin is a good example again. It lands on heads 50% of the time, regardless of which trial it is. Okay, it's independent. It doesn't get more likely as time goes on that you're going to get heads. It's always the same. It's the same with a dice. It's always a chance for 6 that you roll a 6, for instance. So it has to be a fixed probability of success. And each trial has to be independent. If I roll a 6 before in my first trial, it can't mean that it's more likely to get a 6 next time. Each trial has to be independent. We're fine with things like throwing a coin or rolling a dice. There are some examples where we'd struggle for independence a little bit more in real events, like whether or not it rains on successive days. If it rains on a Tuesday and if it rains on a Wednesday, the probability is probably different for each of those. If it rains on a Tuesday, it probably makes it more likely that it's going to rain on a Wednesday, and in turn more likely it's going to rain on a Thursday. Quite often we get lots of rain in a week or hardly any rain in a week. Okay, so That's an example where we wouldn't be able to use the binomial distribution. So there are conditions. There's two really important numbers to the binomial distribution, which we're going to define every time we do a question. That's the number of trials, n, so we call that n. So in the statistical event, I toss a coin 10 times, n is 10. And p, the probability of success for each trial. In the coin example, as long as it's a fair coin, p is 0.5. Okay, so for a coin, a fair coin, I'll say, p is 0.5. For a dice, again, a fair dice, p is a sixth. So that's our probability of getting a 6 or a 1 or whatever it is, but normally we say a 6. Okay, so they're the two important numbers for the binomial distribution. We're always going to state those at the start of every question. So let's have a look at an example. So a fair coin is tossed 3 times. What's the probability the coin lands on heads at least twice? If you watch the tree diagrams video, you'll probably know that we can solve this with a tree diagram by doing something like this for the three times it's tossed. You can figure out the probability. But this is where the binomial distribution comes in really useful. It's kind of okay to do a tree diagram for 3 times, but what about 10? It gets ridiculous. Whereas the binomial distribution is no more complicated really to do. So it's very easy to expand it for larger scale questions. So we had something like this. Does this meet all the criteria? It has to have a fixed number of trials. That was one of our conditions. Well, yes, it does. It's thrown 3 times, tossed 3 times, so there's a fixed number of trials. Each trial has to have 2 possible outcomes, success or failure. That's fine. We've got an outcome of heads and an outcome of not heads or tails, okay? Only 2 possible outcomes. Heads is our success in this case because that's what we want. Tails is the failure. The probability of a trial having a successful outcome is the same for each trial. And it is. It's always 0.5, isn't it? The probability of success, regardless of which trial we're on, is always half. And finally, each trial is independent. And yes, it is. Whether or not it lands on heads is completely unaffected by whether it landed on heads last time. Okay, it's not affected at all by the previous trial. Okay, so it ticks all the boxes, so we can use a binomial distribution for that. Okay, so that's an example where we check whether something can be modeled with a binomial distribution. So writing down distributions now. Again, notation, really important you understand this. The start of every question on the binomial distribution should start with this statement. So what does it mean? Well, x is our discrete random variable. We talked about those at the start. It's the event that we're modeling, so the number of times a coin lands on heads, the number of 6s we get when we roll a dice, the number of children in a class that are boys. Okay, it's a discrete random variable for whatever we're modeling. It can be anything. We're only looking at discrete events. Okay, so we wouldn't say the height of children. That's not a discrete one. That's actually a continuous one. Okay. This little squiggle means is distributed. So what we're saying here is x, our discrete random variable, is distributed with a binomial distribution. Okay, so what we're really saying is we've got this statistical event x for whatever it is, and we can use a binomial distribution to model it. That's what we're saying with that statement. We're saying x is distributed with a binomial distribution, and our binomial distribution is going to have n trials. Okay, so n is the number of trials, and that's the first number we write in the bracket, and p is the probability of success for each trial. Okay, so in our coin example, that would be 0.5. For our dice, that would be a 1/6. Okay, so they're the two important things we have to add to the binomial distribution. Okay. Now, let's have a look at our example again, that a fair coin is tossed 3 times. What is the probability the coin lands on heads at least twice? Well, we can write a statement like this. we're saying X is the number of times the coin lands on heads. That's the event we're trying to figure out. And we're saying X is distributed with a binomial distribution with 3 trials, which we can see from here, and a probability of success of 0.5 because it's a fair coin. So because it's a fair coin, that means that P, the probability of success, is 0.5. Okay, so hopefully you can see where we get N and P from. The reason I'm really driving home this N and P idea is that we need them every time we figure out our probabilities. They're our kind of inputs into the calculation to figure out probabilities.